Hello everyone. I hope that you can hear me okay. My name is Petar Velichkovic, and together with Michael Bronstein, we will be delivering a mini tutorial on geometric deep learning, and which I think is one of the most exciting developments going on in the theoretical categorization of deep learning methods currently. And before we dive into a bit more on what exactly geometric deep learning is, I think it would make a lot of sense to maybe even unpack the very essence of the words geometric deep learning. That is, what does geometry have to do with deep learning? Why do we think it's a good idea to be studying geometry in the context of deep learning, and so on and so forth? And to truly answer that question, I'm going to start this tutorial in a slightly unusual way. I'm going to start by taking you back in time. And when I say back in time, I mean way back in time to, say, the days of Euclid, so 300 years BC or so. As you probably all know, Euclid is the inventor of what is now known as Euclidean geometry. And for many, many, many centuries, it was the only way to do geometry. So if you were doing geometry, it was basically synonymous with Euclidean geometry. And of course, naturally, there were many questions on whether this is actually the case. Like, can we prove that this is the one true geometry? Because it rested on certain interesting postulates, such as the parallel postulates, the statement of, you can see on this slide here in the bottom right, that in a plane, if you have a line and a point not on the line, there's exactly one line that's parallel to it. So many mathematicians tried to show that this is the way it must be done, usually by assuming this postulate to be false and then trying to drive a contradiction. But around the 1800s, something pretty magnificent has happened. Several mathematicians, more or less concurrently, have been able to show that if you assume the parallel postulate to be false, you don't end up deriving a contradiction. In fact, you end up deriving completely new self-consistent geometries. And perhaps the first examples of this were the work of Lobachevsky and Bolyai, which led to the discovery of what is now known as hyperbolic geometry, where actually there could be many lines parallel to a given line in a particular point. And Janos Bolyai is actually famously quoted by writing a message to his father after discovering this concept, that he was amazed. Out of nothing, he has created a strange new universe. And the developments only kept on going from there through the work of others, such as Riemann, that went on further to show that you can also have interesting geometries like the elliptic geometry, where actually there are no parallel lines at all. So certainly the 1800s can be seen as a pretty exciting time to be studying geometry. There were all these different ways of approaching it coming around, each one coming with its own set of terminologies. And, to a new person entering the field and trying to study it, a very natural question to ask really is, what is the one true geometry? What is the model of geometry that we really should be studying? And luckily, the answer to that question came not long after, in fact, a couple of decades later, through the work of this mathematician known as Felix Klein, who through what is now known as the Erlangen program, his research program, when he took up his professorship post at the University of Erlangen in Germany, he basically outlined a blueprint that eventually allowed us to unify all of these different approaches to doing geometry. And specifically through the lens of invariance and symmetry. So you can specify each one of these geometries by making it clear what are the properties of objects that remain invariant under these so-called symmetry transformations. You could quite elegantly formalize it then using the language of group theory. And there is basically no way to overstate how impactful this Erlangen program was, not just in mathematics, but across the sciences. I'll just give a couple of most interesting examples that we could think of. The first one, naturally, it led to a blueprint that eventually allowed us to unify all the different geometries that were in play at the time. And this was primarily formalized through the work of Élie Cartan in the 1920s. But other than mathematics, the Erlangen program had massive spillover effects into physics, primarily through the work of Emmy Noether, who was, I believe, Felix Klein's colleague, and actually showed that using the rules of symmetry and invariance, you can rederive all of the conservation laws in physics. And in fact, some further corollaries of that, primarily through irreducible representations of groups, led to what is now known as the standard model in physics. So really, really foundational work in physics was inspired through the effects of the Erlangen program. And for those of you who might be coming from a more theoretical computer science direction or abstract mathematics direction, one very popular area to study in these areas is category theory, which allows kind of an abstracted way of looking at mathematics through the study of structures. And the very inventors of category theory, Eilenberg and MacLean, in their original paper in 1945, introducing the concepts of categories and morphisms, basically showed and stated directly that in many ways what they've done can be seen as a direct extension of Felix Klein's Erlangen program. So it was one very impactful idea that had massive spillover effects all over the place. And now you might be wondering, why am I telling you about all of this in a tutorial that concerns deep learning, right? What do all of these developments in mathematics, physics, and category theory that happened, decades or centuries ago have to do with deep learning? Well, let's take a moment and think a little bit about what deep learning looks like in this particular day and age. So deep learning around the year of 2020, you have this fantastic explosion of new models and new capabilities working over different types of data. And accompanying these models, you also have certain, let's say, bombastic statements. So you have claims such as everything can be seen as a special case of a convolution neural network, or data usually lives on graphs, so graph neural network is the right abstraction, or transformers use self-attention, and as we know, attention is all you need. Or long short-term memories are Turing complete, so why would you ever need anything else? So there's a lot of very concurrent developments in the area of deep learning, leading to generally super potent models that come from different inspirations, either signal processing or language modeling or network science, and all of those come with different terminologies. And then there's a big question for someone who wants to enter the field of deep learning or to study it more deeply, like, what is the one true architecture? What is the model class that I should be studying that kind of encompasses all the capabilities I'm going to need? And I don't think it's far-fetched to say that the deep learning around 2020 feels a lot like geometry in the 1800s. And if history is to teach us anything, this means that we should try to take all of those salient concepts that Felix Klein introduced that allowed us to unify all these different geometries into one, and see how such concepts can now be applied to the study of deep learning architectures. And another thing which I think will be pervasive throughout both my half of the tutorial and Michael's half of the tutorial is that the graph structure of inputs, and specifically graph neural networks that operate over them, could potentially hold this answer to the one true architecture. Because if you look at the many different ways of passing information in a neural network, fully connected, convolutional, recurrent, or attentive, all of them can be sort of seen as passing messages over a particularly induced graph structure. So there's some way in which graph neural networks could play a part in this one true architecture. But if we want to understand in what way that is the case, we really need to understand them beyond their original construction, which, as we'll see, leverages permutation equivariance. So without further ado, now it is our turn to study geometry. So my name is Petar Veličković. I'm a staff research scientist at DeepMind and an affiliated lecturer at the University of Cambridge. And together with Michael Bronstein and our co-authors, Jean Bruna and Taku Cohen, we set out to do exactly this, to try to take the ideas from Felix Klein's Erlangen program and use them to categorize the deep learning that we have in existence today. We have summarized our efforts so far in a 150-page proto book, which is openly available at geometricdeeplearning.com. What we're going to give you today is a bit of a rundown through the main concepts that the book covers. But if you want way more details, the book itself, auxiliary blog posts, courses, and lectures, the website geometricdeeplearning.com is a fantastic resource that we recommend. Okay, so hence the title of our mini tutorial today. So I'll be telling you about the foundations of geometric deep learning, and then Michael in his second half will tell you about some more exciting geometrically inspired methods that also arise as a consequence of our blueprint. And specifically, in order to be able to introduce the concepts of geometric deep learning, we are first going to take a step back and think about why do we even need all these different architectures, right? Because it is actually a well-known mathematical fact, the universal approximation theorem, that even the simplest of neural network architectures, if they are sufficiently deep, should be powerful enough to fit any real continuous function you want to fit, which arguably could encompass all the meaningful functions you want to learn in machine learning. However, deep learning is typically concerning itself with learning highly dimensional representations of various objects that are given as input. So we often have to do this learning process in high dimensions. And there we hit an issue which is known as the curse of dimensionality, because the way in which we try to learn the target function is by having training data points, here given in red. And basically, the more dimensions we have, we quickly run into intractability issues, even if our target function is very well behaved. So even if you restrict your possible target functions to only be, for example, one Lipschitz, which roughly means the function is not allowed to change too much in a particular point, you can easily see how we can construct this nasty counterexample where you have this, this ball with a bunch of tiny one Lipschitz peaks attached to it. And to properly learn the structure around those peaks, you need a lot more training points around them. And I hope you can see how this problem goes way out of hand when we increase the number of dimensions in which we need to learn this ball. So this is what's known as the curse of dimensionality. As the number of dimensions you're fitting increases, the number of training samples you need increases exponentially. So naturally, we cannot hope to gather such large data sets for many problems of interest. So this is a very important problem for us to be thinking about. And how do we deal with this in deep learning? Well, obviously in deep learning, we still do high dimensional learning problems, and we learn these functions directly by using high dimensional representations. So clearly we found some way to go around this issue. And the way in which we try to summarize all of these developments is the use of geometry. So we have some assumptions about the geometry of the data that we're working with, and those assumptions are injected into our machine learning architecture through what is sometimes known as an inductive bias. But essentially, what is an inductive bias? If you think of the space of all the functions that your machine learning model, your neural network can fit, an inductive bias that's geometrically minded will restrict that space of functions only to the ones that respect the geometry. And this now helps you take your high dimensional problem, which is potentially cursed, and make it more tractable, because even though it's high dimensional, you have a much smaller space of possible functions that you can have in your model. So you're going to need less data to fit it. And that's great for the dataset sizes that you might be having. So here's a few popular examples of geometric assumptions we might want to put into machine learning models. The first one that's very common in the design of convolutional neural networks is that if you have data that lives on images, it should typically be processed independently of any kind of shift. So this cat here should be perceived in exactly the same way, no matter how I choose to shift it around. You can also take these principles and extend them to more exotic domains. So for example, if you have data that lives on a sphere, like this smiley face on the surface of the sphere, it is still the same smiley face, no matter how I choose to rotate it around the surface of the sphere. And naturally, if we have an architecture that deals with data over the sphere, it should ideally automatically build in these kinds of assumptions. And as we said, we're going to be talking about graphs quite a bit today. And in the domain of graphs, a very standard transformation you want to be resistant to is isomorphic transformations. So there's many different ways in which I can choose to present a graph to you, either visually or in terms of the adjacency matrix structure. And here, just one very clear example on this slide, you have these two graphs. Visually, they look very different, but actually, if you stare at it long enough, you'll realize this is exactly the same graph. And ideally, if we build a machine learning model over these graphs, these graph neural networks, they should give us the same answers for these two different graphs because they're actually exactly the same. So those are the kinds of assumptions we typically want to inject into our models. And what we're going to try to do for the first part of the mini tutorial is to try to make this a little bit more formal. So in order to be able to formalize this, we need to agree on some common mathematical framework that we're going to be working with. And specifically, because in deep learning, what we care about is we have some data that lives on a particular space, some domain, and we call that domain omega. And omega is basically just a collection of all of the points of interest in your domain. So if your inputs are images, for example, that you have here, then omega will be typically an n by n grid. So a collection of points in the n times n grid, right? And as we said, you typically want to featureize the different elements of that domain. So for every single pixel of that domain, every single element of the grid in omega, you want to attach to it, well, at least initially, a three-dimensional, usually real representation, which we call a vector space. And specifically in the case of images, the three dimensions correspond to the red, green, and blue pixel intensities of that particular pixel. So now you can imagine that we can define a space of C-valued signals on omega as just the collection of all the functions that take points on omega and tell you what the features are of that particular point. Basically, through this slide where I hope we got interrupted, we were discussing these spaces of signals on a domain and how usually when our domain is finite, so we don't have, or discrete, we don't have infinitely many points. We don't have to think about functions from omega to C. We can actually just focus on the linear algebra way to represent them. So matrices capital X, where the ith row of that matrix gives you the features of the ith node of the domain. And often we might want to assume some additional structure on these feature functions. One typical assumption we might want to make is that these signals form a vector space. So whenever I have two separate feature functions on my domain, X and Y, I can take any linear combination of those, and that is the same as if I first look them up in their individual points and then linearly combine them. And very often it might also be useful to have an inner product defined over these functions. It is sufficient if we have an inner product over our representation space C, and some measure over our domain, then we can compute inner products over these signals in the usual way. So just basically integrate over the entire domain, and at every single point of the domain, take this inner product over C to compose the two features. And in a nutshell, what this means is that the space of all of our signals forms what is known as a Hilbert space. Okay. Now, with that basic mathematical background out of the way, we can chat a little bit more about what is the bread and butter of geometric deep learning, and this Felix Klein approach to geometry in general, which is the approach of using symmetries. And a symmetry is essentially just a transformation of an object that leaves it unchanged. And this is something that's best visualized, pictorially. So in this particular case, you might imagine if your data lives on a domain which is a triangle, and you store features in the three corners of the triangle, then some possible transformations you can do to that triangle, which would leave the triangle unchanged, include rotating it or horizontally flipping it. So that's the R and F operations in there. And what these operations do is they change the way the triangle is presented to you. So what the three nodes actually are, but fundamentally it is still the same triangle. And as a result, we might want to build a neural network that operates over that triangle that is resistant to these kinds of operations. So we'll give you the same result regardless of how much you rotate or flip it. And the very act of saying a symmetry is a transformation that leaves the object unchanged immediately draws with it several important mathematical properties that are undisputable. So first of all, what it tells us is that there must be some identity transformation which leaves the object completely untouched, and that must be a symmetry by definition. Then if I have any two symmetries, I should be able to compose them, and that composition is also itself a symmetry because no information is lost. And further, because the symmetry doesn't change the object, you must be able to invert it, so it must be invertible. And the inverse must also be a symmetry. And when you start to collect all of these different axioms together, you end up realizing that you can discuss symmetries in a very common, elegant mathematical language, which is using the group object. And here I've just outlined the axioms of abstract groups if you haven't come across the term before. So it's basically just a set G, which has these objects that you can also combine using a binary operation, GH. And that operation must satisfy certain properties like associativity must be satisfied of composition, an identity element must exist and transform in the expected way, inverses must exist and compose in the expected way, and so on and so forth. And in case you want to see more beautiful examples of symmetries, here on the right-hand side, you have one of my favorite examples, which are the symmetries of the Rubik's Cube. So once you have a group of symmetries, which is just an abstract object with transformations, what we really want is to talk about how that transformation affects the data that we have on the domain. And that for this reason, we define what is known as a group action. So this is something that takes a group element from G and a point on the domain omega and gives you a different point on omega where the operation of the symmetry moves that point. And the expected axioms of composition and identity must be satisfied in this case. So the identity action on each domain element U leaves it in the same place, and doing one action after another is the same as composing the actions and then applying them. And this is just one example of what a typical group action might look like here in the context of Euclidean planar motion, like translation and rotations. As you probably know, for any particular rotation by theta and translation by tx, ty, you can build a unique three-dimensional matrix that you can multiply with your xy coordinates in a way that will transform those coordinates. And one very important formula that we can get as a result is we can say exactly what happens to a signal x, so some function that takes elements of U and giving you the features on that point U, after we apply the group action G. And specifically what you get is this important formula on the right, where basically you get that it's equal to looking up the signal function in the point U, but transformed with the inverse of G. So what does this really mean? Say in the context of the sphere here, you're actually searching for a point on omega that will end up in U's place once G is applied. And that is exactly the point transformed by the inverse. So when you have G minus 1 GU, you end up with exactly U. So this is a very important formula that allows you to apply group actions also on feature functions. And we will also very often assume that this group action is a linear operation. What does this mean specifically? Whenever we have any summation or combination of two different signals, so say this picture of two different insects, it doesn't matter if you first sum up the two pictures into one and then shift them, or first shift the individual images and then sum the results, you are expected to get exactly the same outcome. And once we have these concepts, now we can talk about one of the fundamental objects in geometric deep learning and also representation theory in general, which are these group representations. So we say that a representation is something that allows us to take this group element G and express what the action of G is in the domain of linear algebra, which is going to be very important for us as deep learning typically operates in the domain of linear algebra. So this will allow us to have concrete mathematical constraints that well-behaved functions need to satisfy in the domain of deep learning. So specifically, we say that a real representation of a group G is this function rho, which takes a group element from G and gives you an n by n matrix such that multiplying your features with this matrix is the same as applying the group action to the data that you have there. And that's why it is very important. Here is one very standard example of a real representation for the shift operation. So imagine you have data that lives on this five-dimensional grid. So the domain omega is just Z5, 0, 1, 2, 3, 4. And you want to be resistant to cyclical shifts. And to do this, you need to create this real representation of a shift, which is this cyclical shift matrix given in the bottom left. And you can also do shifts by up to n spaces by raising this matrix to the nth power. And you can convince yourself the only effect you get when you multiply this shift matrix with your data that lives on omega is that that data will be cyclically shifted by 1 point to the left. and nothing else will change. So it exactly represents the operation that you want to be resistant to in the space of matrix operations. And once you have that, now you can say what it means for some function, like a neural network or any other machine learning model, to exploit the symmetries inside the symmetry group G. So the first important concept is G invariance, which basically says that a function, like a neural network that maps your features on omega to some output y, is G invariant if no matter what group action I take from G, the output is not affected by this action on the input. One standard example of this is in image classification with convolutional neural networks. We typically assume that if we shift the input image, this will not change the output class of the object that's on that image. However, very often we're not just interested in outputs over the entire omega, but we might be interested in predicting something over each element of omega. So in the case of images, this would be segmentation. For every single pixel in the image, you predict which object it belongs to. And here you don't want invariance anymore, because invariance would destroy all that nice structure of individual elements of omega. You actually, when you shift the input, you want your output to change as well, but you want it to change in a super predictable way. Specifically, what you want is a more fine-grained notion of G equivariance, which now says you have a function or a neural network F that takes your signals on omega to different signals on omega, so outputs on omega, rather than just having one flat output Y for the whole input. And we say that it's equivariant if no matter what group operation G I choose, it doesn't matter if I apply it before or after applying my function F. So the group action affects the input and the output in exactly the same way. And you can see this exactly on the example of image segmentation, because a properly built convolution neural network segmentation model, whenever you shift the input by a certain amount, the segmentation mask is forced to shift accordingly. Note that these are hard mathematical constraints that we bake into our models. So this is not something like approximate. It is actually restricting the functions that we want to use to respect these kinds of rules. And convolutional neural networks are, for example, built with this exact property in mind. There's another important constraint. So invariance and equivariance are certainly super important in this scope, but on their own, they still don't restrict the space of functions enough. And specifically, we need to also take into account some realities of processing data from the real world, because even though, say, we built a convolution neural network and it's resistant to shifts, and that's great. So say I have this picture of a house, I transform it with some shift operation, and great, I'm guaranteed that my model will process these two pictures exactly the same. However, in the real world, nature doesn't just apply the symmetry group that we want to be resistant to. So in reality, this house might be a bit shifted, but it might also be distorted or noised in different ways. Now, this operation might still be even a symmetry transformation, but it's not the symmetry transformation from G that we want it to be resistant to. And what happens now, if you're not careful, is any of these noisy issues around every particular pixel, if you're not careful, could immediately propagate to the whole output and make it very numerically unstable. And there's some maths to discuss here on exactly how we can protect ourselves against this numerical instability. But the main conclusion that we derive in the book is that if you want to be resistant to this kind of instability, you need to have layers that are not just invariant and equivariant, but also local. So act only around one particular domain element, or in the case of images, only in the immediate neighbors of a particular pixel. And that way, when there is some noise on a particular pixel, the output is contained to some neighborhood around it. It doesn't immediately blow up everywhere. So this is great for getting stability. And it's basically the essence behind why nowadays modern convolutional neural networks only have small convolutions, like 3x3 filters, but then you make them very deep to propagate the effects throughout your input image. And using all of these concepts, we can now talk about what are some of the building blocks of geometric deep learning. So specifically, in our book, we hypothesize that there are 4 main elements to build geometric deep learning architectures. 2 of them we have discussed just now, so equivariant layers that are also local. These will give us predictions for each individual domain element. And then at the end, in case we don't want predictions for every element of omega, but we want a prediction for the whole output, we can apply a G invariant layer, which is this global pooling operation, as it's sometimes called. And this will give us an output for the whole domain in a way that's resistant to the input operations of G. And we are happy to restrict ourselves to only linear equivariant layers because they are usually much easier to characterize mathematically if we want to build a rigorously equivariant model. And secondly, because in deep learning, we typically introduce nonlinearities in a different way, specifically through the use of this activation function like a ReLU or a sigmoid or something like that, which is applied to every single point in the feature space independently. And that's kind of something we can do after applying each equivariant layer. So we can do an equivariant layer that's linear, then do a nonlinearity pointwise, then another equivariant layer, another nonlinearity pointwise, and so on. For most domains of interest, it's already been well known and proven that if you do it this way, you're bound to preserve all that nice universal approximation properties of neural networks. So this is a totally fine thing to do. And lastly, one thing that we won't discuss that much in this tutorial, but is also an important concept, which arises in, say, pooling layers in convolutional networks. You often might be interested in exploiting the multi-scale structure in your domain. And that's why it might be useful to have an operation that takes your original signal over omega and coarsens it into a signal over some omega prime, which is contained within omega. So this is what we know, what we call as a coarsening or a pooling layer. And taken together pictorially, what you get is a pipeline of the deep learning architecture that looks like this. Here I've used a graph domain omega just to kind of illustrate the most general irregular structure, but you can easily imagine cases where this is an input grid or something like that for the case of images. So you have your inputs, you transform them with a bunch of equivariant layers and some nonlinearities, preserving locality ideally. Then if you want to coarsen the structure, you can apply a pooling layer in between, then follow with some more equivariant layers. And lastly, if you want a prediction over the whole input and not just individual points on the input, then you can have this invariant global layer, which summarizes the whole domain into a signal representation. And it turns out that this is a remarkably powerful pipeline. In fact, essentially what our book is about is showing that using this construction with the right choice of domain omega and symmetry group G, you can rederive basically all of deep learning in use today. So all of the fan favorites like convolutional networks, graph neural networks, deep sets, transformers, and LSTMs can be derived with the right choice of domain that the data lives on and the symmetry group you want your neural network to be resistant to. So they arise as a result of the equivariance and invariance constraints on those particular symmetry groups and those domains. But what's really interesting with thinking in this way is like, okay, so on one hand, it helps us categorize the deep learning that we have so far, much in the spirit of what Felix Klein has done. But then at the same time, it also lets us talk about these more exotic deep learning architectures, which maybe haven't become this popular yet, but are essential if you want to deal with data over more weird domains like spheres or manifolds or even geometric graphs, which we might touch upon towards the end of this part of the tutorial. And this, like following the blueprint in those cases for the specific symmetry groups you care about, gives rise to spherical CNNs for data over spheres, mesh CNNs for data over manifolds, and EN equivariant GNNs for data that lives on geometric graphs, such as molecules or proteins. So you can use these ideas to go on and build more architectures, not just categorize the architectures that are already popular. And that's the reason why we think it's a potentially powerful blueprint. So there's a lot of architectures that we discuss in the context of the book. Some of them I will present to you now. Some of them Michael will present to you in his part. But just as we already discussed, there's many different possible architectures that we can derive through the use of these main ideas of invariance, equivariance, and locality. Specifically, what I want to focus on for the remainder of my part, so for the next maybe 15 minutes or so, is I want to tell you a bit more about sets and graphs. So those are arguably the domains with the simplest geometry, because under no additional assumptions, really all you have is an unordered collection of objects connected together with links, and you have to somehow process the data. But it's also super pervasive. Many real-world, naturally occurring or synthetically occurring data can be best reasoned about in terms of a structure of sets and graphs. So it's definitely a worthwhile pursuit. So let's start with sets. So we're going to assume that we are dealing with a graph with no edges. So our domain omega is just a set of nodes V. And as we discussed, it will be useful to featureize this domain. So we will attach to every node in this set I, a feature vector xi, which is some k-dimensional vector giving you the features of that node. So in this case, our feature space C is R to the k. And there's many ways in which we can choose to present this data to a machine learning model. But one typical way to do it is to stack the node features into a node feature matrix, this capital X, which we discussed before. And it's a matrix of shape, a number of rows equal to the number of nodes, and number of columns equal to the number of feature dimensions. So the ith row will correspond to the ith object. And you should note that the very act of doing so, if we assume an unordered set, is wrong. Because by stacking the features into a matrix, we've suddenly attached an ordering to them, but we don't assume any particular order. So our first goal for today, concretely, is to try to use the principles of geometric deep learning to build a neural network that will be resistant to this particular choice of ordering. So what do we want is something like this. If I have a function, a neural network F, that produces outputs for given input sets represented as feature matrices, I should get exactly the same response no matter how I choose to perturb those different features in my set. As long as it's exactly the same set, I should get the same answer. And the symmetry group in this case turns out to be the n-element permutation group. So how do we arrive at that? Well, our features come in the form of these matrices. It'll be useful to think of operations that change the order of the nodes, so the order of the rows. And those operations, as you know from combinatorics, are known as permutations. For n objects, there's n factorial, many of them. Here is just one example of a permutation of 5 objects. You can also numerically code it as 3, 2, 4, 1, 5. And we can use the theory of real representations that I already mentioned to claim and show that within the realm of linear algebra, every single permutation defines a unique n by n matrix, which allows you to perform the permutation in the linear algebra space. And that's known as a permutation matrix, or the real representation of the permutation group action. These permutation matrices are very special. Here you have one example for a particular permutation, 2, 4, 1, 3. And you can see they have zeros almost everywhere, but a 1 in every row and column. Such that when you left multiply that matrix with your node feature matrix X, the only effect that you get is that the rows get permuted, but everything else stays the same. So it's an excellent abstraction for what we want to do here. And specifically, this then lets us arrive at a general blueprint for learning on sets to have this invariance and equivariance properties that if I apply a permutation matrix P to my input features, it doesn't matter if I do them before or after. This will give me equivariance. And in fact, the only way to enforce this in a local way without assuming additional structure is to process every set element in isolation. So I have to have this one function, this one neural network psi, which is applied in a shared manner to every single node feature xi to get latent features hi. And then if I want to get predictions for the whole set, I need to combine these outputs hi in a way that is invariant to permutations. And one way in which we can do that is by summing all of them or applying any other kind of permutation invariant operation, which we denote by this O plus. So whenever you see an O plus, it basically means a sum, a maximum, an average, anything which doesn't depend on the order of its inputs. And then we can apply another function phi to process this. Note how this form, the model which is known as deep sets, lines up perfectly with our geometric deep learning blueprint. You have a stack of equivariant layers in blue. And then if you don't want to predict over individual set elements, but the whole set, you just append this invariant tail at the end. And that's it. Anything beyond this, like anything which uses more than just xi in psi, would no longer technically be a set because it uses some graph structure. So it will be meaningful to think about how we can move on from sets to graphs. But before that, let me note that these ideas from deep sets are not just pervasive in abstract set analysis, but they've broken into computer vision where they're regularly used to process data that lives on point clouds. And specifically, deep sets models that are applied in the point cloud domain are often known as point nets. They were developed pretty much concurrently to deep sets. And as you can see in the picture here, the structure of a point net is basically the same idea as deep sets. Transform every point in the point cloud separately, and then at the end do a pooling operation. In this case, they use max to get global features to classify the entire point cloud. So now that we have a basis of understanding how to do learning on sets, we can extend this in the final part of the tutorial for my side to talk about learning on graphs. So now we don't just have the nodes V, but our domain also has a set of edges E, which is the subset of the Cartesian product of the nodes with themselves. So it's the set of all connections between the nodes. There's many ways to represent them, but since we're in the domain of linear algebra, I'm going to find it most convenient to continue to use this adjacency matrix formalism. So we're going to have an adjacency matrix, capital A, such that it has a shape of nodes times nodes, and ones where we have an edge between the two nodes and zeros otherwise. There are many other things we can do here, especially in the domain of molecules. We can put edge features or edge distances or something like that. Those are all possible, but to keep the math simple, we ignore them without really losing any generality. And the main desiderata that we have, really, without assuming additional geometries, which is what Michael will talk to you about in the second half, the main things we want, permutation invariance, permutation equivariance, are still there. So what's really changed? Previously, in the domain of sets, we wanted to have a neural network that will process these two sets in the same way, no matter how I choose to permute the elements. What's different in the case of graphs? Well, not much, really. It is exactly the same picture. The only difference is that now I also have these edges connecting the nodes. And whenever I permute the nodes, I must permute the edges accordingly. That's the only thing that's really different. So we can basically take the rules for permutation, invariance, and equivariance over sets and modify them to get the same rules over graphs. So we can now, the only difference is that our functions f now need to take into account both the node features x and the adjacency matrix A. And whenever we apply a permutation matrix to x, we need to also accordingly apply it to A. Since we said A is a matrix of nodes by nodes, we need to permute its rows and its columns. So that gives you this PAP transposed. And otherwise, it's exactly the same. So permutation invariance, if I permute the input, same output. Equivariance, if I permute the input, I get the same output, only permuted. Now, note that here I've subtly assumed that our equivariant layers only update the node features and not the adjacency matrix, which allows me to directly apply P to the output of F. But in reality, there are also many interesting developments on neural networks that also change the adjacency structure. We're just not discussing them in the context of this tutorial. But there's more details in the book if you're interested. But the one main thing which is different in terms of graphs versus sets is that, as we said, in sets, you kind of assume it's a bunch of objects floating without any relation to each other. But now you have these edges connecting the objects, which lets you enforce locality more clearly by just transforming every node together with its neighborhood. And there's many ways to define a neighborhood. We typically define it using this NI notation. So the neighborhood of node I is just the set of all the nodes that it's linked to with an edge. And then we can extract the set of all the features in this neighborhood, the multi-set of all features in this neighborhood, x and I, by taking all the xj vectors from j being the neighbors of I. And now our local function can look at not just the xi, but also all of the features inside x and I, therefore making it local. And once you have a layer like this, you can then apply it separately to every single node's neighborhood in isolation, stack the results together in a new node feature matrix, and voila, you have yourself a permutation equivariant graph neural network, right? And there's one more condition that we need to make sure that this function is equivariant, because the local function phi deals with the multi-set of neighbors. We need to be careful that it doesn't depend on the order in which those neighbors are presented. So we can easily prove as long as the function phi is built to be invariant to x and I, then the whole function f obtained by stacking the results of phi will be permutation equivariant. And this is a lot of terminology which was potentially presented quite fast, and I think it's a good moment to take a step back and just visualize what is it that we have just derived using the basic principles of geometric deep learning. We've built a basic structure of a graph neural network. So the way graph neural networks work is you take a feature of a particular node in a graph, you take the multi-set of features of all the neighbor nodes, and then your graph neural network takes all of that into account to update the features of that particular node to get this latent vector HB. And once you have that, you can do any learning task on a graph by directly following the geometric deep learning blueprint in the appropriate way. So you have some graph inputs with node features X and adjacency matrix A. You apply your GNN, which is a permutation equivariant layer that focuses on the locality of each node, the immediate neighbors. What it does, as we said, we assume it transforms the input features to some latent space H, It typically doesn't change the adjacency matrix, although that is also possible. And then based on what you want to do, if you want to classify individual nodes, you still want an equivariant prediction. So you just slap on some equivariant classifier on top of everything. If you want to predict over entire graphs, like graph classification problems, then you can still do that, but you must do it in a way that's invariant to permutations. So basically, you need to first reduce all of your node features using some permutation invariant function, such as summing, and then feeding that summed feature into a classifier. And lastly, another interesting equivariant prediction you can do is over edges. You could even predict whether or not an edge exists, which is why this task is typically called link prediction. So once again, you can learn a local equivariant classifier, which takes into account the features of the two nodes I and j that you're looking at, and maybe some edge features between them if you have them. And that's the way to build link prediction. And this is the essence behind 99% of graph tasks in use today, derived entirely using the basic principles of invariance, equivariance, locality, and the geometric deep learning blueprint. And note that I have told you this without really telling you how to implement this local function phi based on which everything is built. However, in the book, we have a detailed discussion of this, and we categorize the different phis into 3 flavors. Needless to say, it's one of the most intensely growing areas of deep learning right now, defining different phi functions. But fortunately, most of them can be nicely categorized into convolutional, attentional, or message passing operations. We don't have enough time to go into details on them, but as you go left to right, their expressive power increases, so they're able to fit more complicated functions, but it comes at the expense of scalability, so they require more complicated operations, and it comes at the expense of interpretability. It's harder to interpret how they're making their decisions, and it also is a bit of a risk to overfitting because they have more parameters. They might have problems learning certain classes of functions, especially if they're simpler. And before I wrap up my part of the tutorial, because I would like to also give some time for questions, I'm going to make a quick note on the transformer architecture, because if you take this generic formula for the attentional layer that you have here in the middle, here you have basically a function of a node's features and then aggregated combination of neighbor transform features, psi of xj, multiplied by a scalar coming from an attention mechanism. This feels a lot like a transformer. And actually, if you just make one more change saying that everything is connected to everything, you can rederive the entire transformer architecture as a fully connected attentional graph neural network. And this discovery comes at no surprise, really, because words in a sentence, so transformers are typically introduced in the context of language processing. Words in a sentence typically interact in complicated, non-trivial, non-sequential ways. And therefore, there is some interesting graph structure between the words, but we don't know what that graph structure actually is. And it might be really interesting to try to learn it. So what we typically do in graph representation learning is then we just assume everything is connected to everything. So this O plus here arranges over all of the nodes, not just the neighbors. And then let the graph neural network figure out by itself what the graph should be through these attention coefficients, right? And therefore, you can imagine the transformer's attention mechanism as a sort of way to infer a soft adjacency matrix and basically letting the graph neural network choose its own edges. I think this is a really fascinating result that I would love to go into more detail, but it's not really within the scope of this part of the tutorial. But I will point you to this fantastic blog post from Chaitanya Joshi that was published in The Gradient. It's titled Transformers or Graph Neural Networks, so it's very easy to find, which goes very much in depth on how you can directly relate the operations of a transformer to the operations of a attentional graph neural network. And on that note, in order to leave some time for questions at the end, I'm going to skip over the parts talking about geometric graphs, which kind of extend this to work over molecules and the Euclidean group, and maybe also linking it a bit more to the context of manifolds and parallel transport, which I think Michael will also discuss to some extent in his part. So on that note, just to kind of summarize what we've seen so far, we've seen the geometric foundations of neural networks and specifically how they apply to the domain of sets and graphs. So we've seen that you can build most of today's or all of today's deep learning architectures by carefully specifying a domain, specifying a symmetry group, and then building your model to be invariant, equivariant, and local within that domain. And specifically, we showed that in the domain of sets, taking the permutation group as your symmetry group, you can rediscover the deep sets model for permutation equivariant learning over sets. And then you can rediscover graph neural networks as permutation equivariant models over graphs. And then additionally, we saw how transformers, one of the most popular deep learning architectures in use today, can be discovered as a special case of a fully connected graph neural network of the attentional flavor. And we glossed over there some connections that allow us to compose the permutation group with other groups, allowing us to build stuff over geometric graphs, manifolds, and meshes. Before handing it off to questions and eventually to Michael, I'd just like to note that we are very actively trying to improve this proto book of ours. We have an agreement to get it published in 2023 with MIT Press. So if you have any and all feedback that might help us, this is actually the best time to intervene meaningfully in the development of our book. So if any of this, in either my part or Michael's, piqued your interest and you'd like to learn more, either in the form of book, blog post, lectures, or talks, you can find all of those resources and more at geometricdeeplearning.com, which I once again point to you. And I'd like to thank you once again for inviting us to deliver this tutorial. We hope that you have enjoyed it so far. So I will stop there and maybe take 5 minutes for any questions while Michael sets up his part. So are there any questions from the audience? Okay, I see there is one question already in the chat, so I will start by answering that. The question comes from Vignesh, and the question asks, has the paradigm of GDL led to discovery of new architectures yet? I think this is a very important question. I would say that it definitely has, and we have seen the most developments in this direction, I think, coming from researchers who are building models over molecules. So this is the part that I had to glance over, where other than just the permutation symmetry, you also have some spatial symmetries like the Euclidean group acting over coordinates of the molecule, of the atoms in the molecule. And these lead to very interesting product groups that you might want to be equivariant or invariant to. I'm sure Michael will also discuss some of these in his part. So as far as we are aware, the people who invented these new architectures have directly cited our blueprint as one of the inspirations for how they built it and explained it. So to the extent that we can claim this, I'd say it definitely led to the development of novel architectures there. Another area where I think people have been quite inspired by our work was the domain of quantum machine learning, where people are trying to build machine learning models to run on quantum computers. And there, as you know, state-of-the-art quantum computation is very memory bottlenecked. You only get a handful of good qubits in a quantum computer. So to be able to make advantage of those parameters as best as you can, you really need to bake in symmetry assumptions. So a really fun thing happened where I think 3 separate groups doing quantum machine learning have published their own quantum versions of the geometric deep learning blueprint pretty much in the same week. So I would say those are the 2 maybe most interesting domains that I've seen so far. Probably Michael will mention a few more, but thanks for the question. I think it's a very good one. Yeah.
Hi, thank you for the talk. My question is about LSTMs and sequentials where the order does matter, and then also how that applies to like regression tasks. Because I know, or at least a lot of the literatures, where we have things that are invariant for shifts because it's a classification, but when we have where order matters and we're looking for a regression, these invariances don't exist, or maybe they do, and I'm just thinking about it incorrectly.
Yeah, that's a great point. So I'll just quickly scan back to the table of architectures so we can look at it together. Basically, yeah, we do cover LSTMs, and as we say here, it's a one-dimensional kind of oriented grid. As you said, there is an order temporally, and it matters. And in fact, the symmetry group here is not really translation equivariance anymore. It's possible to make it happen, but you need to do some wacky stuff to the input. Actually, what we found, and this was another recent work that came about from Corentin Talek, that you can rediscover LSTMs and the whole class of gated RNNs through what they call time warping invariance. And what this means basically is when you have this like temporally sampled signal, there's arbitrary time dilations that can happen in the sampling of that signal, right? Your sampling rate may dynamically change as you do it and so on. And you ideally want your model to be resistant to those kinds of sampling changes. And if you analyze these temporal models from this perspective using some Taylor series and differential equations, you end up discovering that in order to be able to adapt dynamically to the changes in sampling rate, you need to be able to fit what they call the time warping derivative. So some function that takes your inputs so far and gives you kind of a number between 0 and 1 saying what's the derivative of the sampling rate so far. And it turns out that what you've just discovered is a gating mechanism. And it turns out, gating mechanisms are basically the bread and butter of not just LSTMs, but also GRUs and other kinds of, very influential machine learning models. So we actually found that LSTMs are much nicer talked about in terms of time warping invariance, but fully like these kinds of unordered invariances that we discussed so far would not apply for them. So yeah, I hope that answers your question.
Thank you.
I see there's one more question on the chat from Vasileos. So how about higher relations in graphs? I'm going to assume that higher relations in graphs refers to hypergraphs or hyperedges. So basically edges that could have more than 2 nodes participating in this relationship. It is a very interesting topic that I'm sure also Michael can tell you a lot more about. But essentially, you can still talk about permutation symmetries in hyperedges. You just need to, if you want to model them explicitly, you need to include hyperedges as part of your domain, and you need to be careful. So in the case of pairwise message passing, we can also look into this one more time. You had these different ways of incorporating messages from your neighbors. Now you need to be careful. Now your psi function here might take into account not just xi and xj, but also some third node xu or something. And you need to be careful, depending on the symmetry assumptions of your domain, in what order you're going to feed those values in and do maybe make it commutative or something like that. So these are the kinds of considerations you might want to do. Although I will make one remark on hypergraphs in that if you want to model this kind of higher order information, I do have some recent paper that shows that to some extent you can model this using a pairwise message passing model, but you need to modify your input graph to like invent a new node for the hyperedge and carefully link it to all the constituent nodes and stuff like that. So yeah, the GDL framework definitely still applies. You just have to be a bit more careful because there's more objects in the hyperedge. Yeah, thank you all for these fantastic questions. I think in the interest of time, I should hand over to Michael. So Michael, if you're keen to start sharing your slides, please proceed. And if you have any more questions, please feel free to reach out to me via email. Thank you so much.
Thank you, Peter. I hope you can see my screen. So maybe just one short remark to the previous question. So there are generalizations of message passing to structures that are more general than graphs, such as simplicial or cellular complexes. So these are hypergraphs with more structure. So one example would be triangular meshes, and this is actually what is used in, for example, in computer graphics and geometry processing. So short answer, yes, you can derive these models from the same blueprint. So in the second part of the tutorial, I would like actually to focus on a topic. I would not go into other instances of the geometric deep learning blueprint, as Peter in his part alluded. We can also apply it to objects such as spaces where the group acts transitively, so homogeneous spaces like the sphere. We can also apply it to manifolds and meshes. We can also apply it to time sequences. I would like to talk maybe to something that would appeal more to the audience of SIAM, which is relating graph neural networks to differential equations and physical models that are described by these differential equations. So this is a relatively new topic, even though it exists in machine learning for quite a while, but probably applied to graphs. This is something that has come up in the recent years. So just to give a motivation why and how graphs are different from other objects that we are treating in this blueprint, if you compare, let's say, graphs versus meshes versus grids. So one thing that characterizes a grid, that if I look at the neighborhood of a node, then I have a fixed order of my neighbors, right? I can talk about, for example, a neighbor on the top and a neighbor on the bottom. And for every node in the grid, it will be the same. On a mesh, I have slightly more ambiguous situation. So I can say that I fix the first neighbor, and then starting from this neighbor, I can enumerate all my neighbors, for example, in clockwise orientation, and meshes are discrete manifolds. So we have this way of doing it. Now, on a graph, as we've seen in the previous part, any permutation is allowed. So in a sense, they have the least structure among other objects. Now, another thing that you will notice is that, again, if we look at grids, meshes, and graphs, then I can think of grids as discretizations of the plane, or of meshes as discretizations of manifolds or surfaces. We don't have this immediate analogy for graphs, so they're kind of inherently discrete, and of course, this sounds a little bit unfair. Can we have some continuous model for graphs, or maybe more general for graph neural networks? Can we derive graph neural networks by discretizing something continuous? Now, what Petra didn't mention, also there is a deep link between graph neural networks and theoretical results in graph theory. And this is actually how graph neural networks, or maybe precursors of graph neural networks, appeared in the 60s. And they were motivated by problems in chemistry where you have molecules and you try to determine whether molecules are structurally similar. So this resulted in the work on graph isomorphism testing. Basically, the classical result there is the algorithm devised by Andrei Lehmann and Boris Weisfeiler, where they showed an iterative algorithm that does color refinement on a graph, trying to determine whether two graphs are isomorphic, if they are structurally equivalent. So the way that this algorithm proceeds is the following. So we start with the graph where every node is colored in the same way. So by colors, I refer to discrete labels. And it looks for different neighborhood structures. So initially in this graph, you can see that we have two types of neighborhoods. We have a blue neighbor with, a blue node with two blue neighbors and a blue node with three blue neighbors. So the message passing paradigm that we've seen before would say that I will need to aggregate the information from my neighbors using some permutation invariant function. So if this function is chosen as an injective function, then I can guarantee that different neighborhood structures will be assigned different color. So this is the color refinement procedure, and I can repeat it again. So now we have three different neighborhoods, and if I repeat it again, then the colors will not change. At which point I can output the distribution of different colors of the nodes, and this will be a kind of graph descriptor. And if I give you another graph and we repeat the same procedure for another graph, and I get a different distribution of colors, I can guarantee for sure that these graphs are not isomorphic. But if the distributions are the same, we actually don't know. And this appears to be a necessary but insufficient condition for graph isomorphism. You can find easily examples of not isomorphic graphs that would be deemed indistinguishable by this procedure. And one example is shown here, and you can actually see why it happens, because this test constructs rooted trees around every node, and it happens that in this graph they look the same. So one simple trick to make message passing graph neural networks that are actually formally equivalent to the Weisfeiler-Lehmann graph isomorphism testing is to add some information to the nodes of the graph. And Petra mentioned transformers. In transformers, this is done in the form of positional encoding. So you label the nodes with some extra features telling where this node is located on your domain. And for example, we can even attach random features to every node of the graph, and this will break this regularity that confuses the isomorphism testing algorithm. You can do smarter things. You can count structures like cycles or triangles. You can also, answering the previous question that was asked about higher dimensional or higher order structures. So you can also lift the graph into a cellular or simplicial complex. So you can say that I am regarding, for example, triangles as higher dimensional objects, and I can do message passing between nodes, between edges, and between triangular faces, for example, on the mesh. So bottom line, there are many different graph neural network architectures that take the graph into enrich its structure with either positional or structural encoding. Now, another thing that you need to notice is that the graph has dual role in graph neural networks. So it's part of the input together with the node or possibly edge features, as well as a computational device, because you use the graph to propagate information using the edges of the graph. And some graphs tend to be unfriendly for message passing. As you can see here, for example, in this graph, we have a bottleneck. So if I need to send information from one cluster of nodes to another cluster of nodes, I need to squeeze a lot of information into just a few nodes, and it becomes very inefficient. It's difficult to learn. So the standard remedy in the literature for this is to do graph rewiring. So I would allow to change the structure of the graph in a way that facilitates message passing and makes the graph more friendly. And I would say that de facto, most of graph neural networks that are used nowadays use some form of graph rewiring, whether it's in the form of neighborhood sampling, or maybe in the form of virtual nodes or virtual connections. So there are many techniques that do not stick to the original graph that is given as the input, but do some modification to it. So of course, what we want to understand is how to do these things in a principled way. For example, what would be a more principled approach for positional encoding, or how to do graph rewiring. Now, the metaphor I would like you to have in mind for the remaining part of this tutorial is thinking of learning on graphs as a physical system. So we can think of GNN as a dynamic system, and what is shown here is a system of mechanical oscillators in every node of the graph that are coupled by the graph structure itself. So you probably have seen these videos where you have metronomes standing on a table, and initially they're all out of sync, but eventually they become their oscillations become synchronized. And that's exactly this kind of situation where you can think that standing on the table, there is coupling between all of them. So we can think of more general coupling functions that allow basically that are described by a system of differential equations that governs this system. So graph neural network, we will be thinking of it as dynamical system that will be discretizing. So the layers of the neural network will be discretization of time. And in some situations, we can also think of the graph as a discretization of some continuous objects, of some spatial object. So this view actually is not completely new in machine learning. So there is a plethora of works on thinking of deep neural networks as partial differential equations. So I mentioned two probably most famous. One is by Lars, another one by the group of David Duvenot on neural ODEs. And we are following similar ideas, but for deep learning on graphs. So if you think of what kind of physical systems or physical processes you might consider when you want to model propagation of information, so the first thing that will probably come to your mind is the process of diffusion. And diffusion has been studied rigorously, probably for the first time, by no one else but Sir Isaac Newton. He published it anonymously in the Transactions of the Royal Society in 1701. He would become Sir Isaac 4 years after. And there he formulated what is nowadays known as the Newton's law of cooling, saying that the temperature that a hot body loses in a given time is proportional to the temperature difference between the object and the environment. So it's a kind of global rule that tells you how objects cool down. So it took about 100 years before this was formulated more rigorously in the modern terminology of differential calculus. So this is called the Fourier heat conduction law, published by Fourier in his classical book on the analytic theory of heat. And there he defined heat flux that results from thermal conduction, saying that it's proportional to the magnitude of the temperature gradient and opposite to it in sign. And finally, another part that is missing is what is called the Fick law of diffusion. So Fick was actually started as a prosector. Basically, he was dissecting dead bodies, but he studied chemical diffusion. And his law is that temperature change in time equals to the heat flux through volume that mathematically is modeled as the divergence. So it's a kind of conservation law that tells us that heat is not created out of nowhere and doesn't disappear. So put all together, we get the classical diffusion equation. So we have some quantity, let's say temperature, in our on our domain and on our object. It creates heat flux that is proportional to the negative gradient of the temperature. the conservation condition means that the only change in time is due to the divergence of this heat flux, and put together, this gives this classical equation. So on the left-hand side, we have the temporal derivative of our quantity, temperature. On the right-hand side, we have divergence of the gradient, and we also have the diffusivity function that I denote here by A, that models the heat conduction property of the domain. So in the simplest case, we can assume that this A is constant, and then I can take it out of the equation, and I get what is called homogeneous diffusion. So this is the simplest form of the diffusion equation. You can also see it as the gradient flow of the Dirichlet energy. So we'll talk about it a little bit later. Basically, this energy decreases monotonically along this equation, and Dirichlet energy measures the smoothness of a signal. So it is intuitively coincides with the intuition. As we diffuse more and more, things become smoother, right? So at the end, we'll get some constant distribution of temperature. In the Euclidean case, you can also write a closed form solution to this simple isotropic diffusion equation as a convolution with the Gaussian filter. And the variance of the Gaussian is proportional in time. And again, you can think of it as a kind of low pass smoothing filtering of your signal. Now, you can, of course, consider more interesting forms of the diffusion equation that are where the diffusivity is position dependent. So this is called non-homogeneous diffusion, or even direction dependent. So this is called an isotropic diffusion, where we have the diffusivity as a matrix that locally scales the gradient of the temperature. Now, these kind of equations attracted a lot of attention about 30 years ago in image processing and computer vision, starting from the seminal work of Pietro Perona and Jitendra Malik in 1990, where they made an analogy between diffusion equations and low-pass filters, trying to remove noise from images. So you see the image, the face of Sir Isaac on the left. If I want to remove noise, I will just apply a linear filter, something that looks like Gaussian. It will average out the noise, but of course, it doesn't look nice because I have also averaged out, I mix together pixels with different intensities. So these destroyed sharp discontinuities in the image that are important for visual perception. So the idea of Perona and Malik was to use a diffusion that is adaptive. So we have a diffusivity that is inversely proportional to the norm of the gradient. And in other words, this diffusion senses a discontinuity in the image and slows down or stops the diffusion. And you can see how the kernel of this diffusion equation looks like. And the result is shown here on the right. You see that we average in piecewise smooth or piecewise constant parts of the image, and we stop the diffusion when we see discontinuities. And this has attracted a lot of interest. It is a very elegant idea. You can actually think of an energy that models somehow the quality of your image, and you can write optimality conditions for it in the form of, for example, Euler-Lagrange equations, and you minimize it using a partial differential equation. So you have some evolution of the image that flows you towards the optimum. And there were entire books and conferences on variational or PD-based image processing, and all of these were almost entirely wiped out by the advent of deep learning. And one of the reasons is that it is difficult to come up with these functionals or equations that would be suitable for any kind of data, right? For every image. So unlike deep learning, where you can learn from examples. So what is happening in the field of graph neural networks is that there is recent revival of some of these methods in the context of graph learning and using modern techniques of deep learning. So if we look at the diffusion equation on the graph, we can write exactly the same equation that formally has all the ingredients that we've seen before. So the gradient on the graph is just the difference between the features at two endpoints of an edge. So xj minus xi. The diffusivity function, this is the attention that Peter mentioned in his lecture. And the divergence will be just summing all the edges that share a node. So we get a nonlinear differential equation. In order to solve it, we need to discretize it. In the simplest case, we can discretize it with just taking steps with constant step size that I denote here by tau. And we get we replace basically the temporal derivative with forward difference. So this gives explicit or forward Euler scheme. And you see how the iteration looks like. So if I slightly reorder the terms here, I get a familiar expression that we've seen before in the first part of the tutorial, which is a graph attention network. So here I assume that the diffusivity is normalized, so it's stochastic, and this can be interpreted as attention. And we are assuming here that the time step size is tau equal to 1. So you can see that graph attention is a particular discretization of graph diffusion. And of course, we don't need to stop at explicit schemes. We can also use implicit or multi-step adaptive step size schemes. So in the field of numerical analysis over the past 150 years or even more, there is a plethora of different methods to solve these type of differential equations. And the way that it can be applied in learning problems. So let's say that you want to do node classification or node regression. So you start with some features in the nodes of the graph that can be potentially encoded with some nonlinear encoder that I denote here by phi. Then you solve the graph diffusion equation using an iterative solver, evolving the initial features until some time t capital. And the diffusivity function here is parametric. So this is what we parameterize, and the parameters are learned in the standard way using backpropagation, depending on the task that we are trying to solve. And then we read out the result of the diffusion, possibly followed by some nonlinear and nonlinear decoder. And what it gives is a new perspective on all problems, as we'll see, problems like oversmoothing and bottlenecks, but it potentially allows to design new architectures, not only interpreting existing architectures such as GATT as discretization of the graph diffusion equation, but also using, for example, more efficient solvers such as multi-step or adaptive step solvers, multi-grid solvers, and so on and so forth, that, at least to my knowledge, currently do not have exact analogs in the zoo of different graph neural network architectures. We can also benefit from some theoretical results such as stability or convergence guarantees, and as I hope to show you in the rest of this tutorial, also deep links to other fields that are probably less known in machine learning, or in particular in the GNN literature, such as differential geometry and algebraic topology. So one example where this kind of view is beneficial. So one issue that is associated with graph neural networks is that it's difficult to make them deep for a variety of reasons. One of them, for example, is the phenomenon of oversmoothing. So here we don't have depth in the traditional sense of deep learning, in the sense of the number of layers. So here we can talk about the diffusion time. And if our steps are of constant size, then of course we can relate one-to-one the depth or the number of layers to the diffusion time. But if we use other solvers with adaptive steps, for example, then we can afford to make bigger steps using less iterations or less layers. And we see that we can, with these diffusion equations, we can avoid the problems of deeper architectures, so we don't experience the same drop in performance as standard architectures would see. And well, some examples of evaluation of this scheme on some of the standard benchmarks from OGB. So you can see that it performs better on par, at least at the time when it was published. What is interesting to see that actually we use here shared parameters. So every layer or every iteration uses the same parameters. So if you compare, for example, this architecture with GATT, then it will have something like 20 times less parameters with similar performance. Now, I still didn't deliver on the promise, so we wanted to consider graph neural networks as discretization of some continuous systems. So far we discretized the continuous time. We didn't discretize the graph itself, right? So we didn't get the graph as a discretization of something continuous. And if I go back to my original Euclidean diffusion equation that I solve on a grid, so here, for example, if I discretize the second order derivative of the Laplacian operator, I can see that there are many ways of doing it, right? So here I show 3 examples, or any convex combination of these discretizations that is also a valid discretization of the Laplacian. So what I'm trying to say is that we don't really have any canonical graph in diffusion equations in the Euclidean case. And what I'm trying to convince you is that we can try to adopt the same mindset for on graphs as well. So we do have a graph, but we can change it as is convenient numerically or otherwise in our given problem. And in order to get an idea of how this can be done, instead of looking at the nonlinear diffusion that we've seen before, we can look at a non-Euclidean diffusion. So in this case, again, these are methods that were developed in image processing about 30 years ago. So we can consider an image as a manifold that is embedded in some space that is a joint space combining positional coordinates, the XY coordinates of the pixels, with the feature coordinates, for example, R, G, and B channel. So a color image will be a two-dimensional manifold or a two-dimensional surface living in R5, right? You have the coordinates are X, Y, R, G, and B. And by virtue of this embedding, we can define a special metric, the pullback metric on this manifold. And with respect to this metric, we can define an analogy of the Laplacian operator that is called the Laplace-Beltrami operator. And a diffusion equation with this operator is called Beltrami flow. It's a gradient flow of a generalization of the Dirichlet energy that is called the Polyakov energy or Polyakov functional. So it is harmonic energy that is used in high energy physics in string theory. Yeah, so there is a comment that it is possible to consider a continuous version of the graph structure via the notion of graphon. So it's a very interesting comment. Actually, one of my collaborators, Ron Levy, he used this notion in a recent paper as well as some of our previous joint papers where we proved stability of spectral graph neural networks using exactly this kind of formalism. Yeah, so thank you. This is important. So basically, what we can do for images, we can also apply to graphs. And in this case, we can think of a graph as every node having two types of coordinates. So we have a positional component that I denote by U, and a feature component that I denote by X. And together, I denote these coordinates by Z. And the positional coordinate can be any positional representation of the graph. So it can be some embedding in some continuous space. It doesn't need to be Euclidean. Typically, graphs are better embedded in spaces with hyperbolic geometry. And we can evolve both, right? And the evolution of the feature component is what we've seen before. So this is feature diffusion. But the evolution of the positional component, you can derive from it some form of graph rewiring. Because if I see that two nodes in a graph, their positional coordinates become closer as a result of this evolution, I can decide to put an edge there to facilitate the propagation of information. Or if they drift apart, I can decide to disconnect the edge. And maybe it's a little bit cumbersome to explain. So I think this image or this video illustrates it much better. So what you see here is a small graph that is called Cora. So it's a citation network. Every node here, the color represents some low dimensional projection of the features. The position of the circle represents again, two-dimensional positional coordinates. And what happens here are three phenomena at once. So we're diffusing the features, so the color is changing. We are diffusing the positional coordinates, so the nodes move. And the graph is also rewired on the fly, so the connectivity changes. And this is how it works. Now, I mentioned the notion of gradient flow, and it's worthwhile to devote some more time to it. So if we have a dynamical system whose state is evolved by this system of differential equations, so we have some f, right, that acts on x, and we have a temporal derivative of x in time, right? So x will be, for example, the node features, and f will involve some coupling through the graph. We say that this evolution equation is a gradient flow if there exists an energy that I denote by E, such that this f equals to negative gradient of the energy at every point of time. And the energy monotonically decreases along the flow. It's very easy to see, right? And it gives us some form of physical interpretability, because usually these energies will correspond to some well-known and well-understood physical systems. So we can say, for example, that our graph neural networks performs some form of dynamics of physical system. And we can prove some properties. We can say, for example, that these dynamics has low frequency nature, high frequency nature. We'll talk about it in a second. So the prototypical gradient flow, we've seen it already. So this is the heat equation. So on the graph, we have an energy that we call the Dirichlet energy, right? So it's essentially, I look at the gradient of the signal on the graph. I take the norm of the gradient and I sum over all the edges of the graph. I can also express it in matrix vector notation as the trace of this quadratic form with the graph Laplacian operator. Now, what minimizes this energy is the graph heat equation. So the standard equation that we've seen before. So temporal derivative on the left, Laplacian on the right. And I already said that Dirichlet energy measures the smoothness of the signal or the features on the graph. So as a result of this evolution, because the Dirichlet energy monotonically decreases, features will become increasingly more similar. So at the end, all the features will be the same. So this is a phenomenon that is known as over-smoothing in graph neural networks. So graph neural networks of this simple type are believed to be over-smoothing the features. So features will collapse into the same point in the feature space. Now, what is important to see here is actually in this diffusion equation, every channel is treated separately. So maybe you can see it here. If I write this equation coordinate-wise, you see that when I'm making the updates in time, right, I am not mixing channel K and J. It's always the same channel. And it is also intuitive. So in images, for example, we never mix, let's say, R and G channel. It would not make sense. But when we are talking about features in graph neural networks, it actually might make sense to combine some of the features, for example, with the linear transformation. And this was a classical architecture that is called graph convolutional network, or GCN. And graph convolutional network consists of two things. I can do diffusion. So I'm mixing the features from different nodes of the graph along edges. So here the diffusion is typically either the Laplacian or the normalized adjacency matrix of the graph. And I can also do shared node-wise channel mixing. So I'm multiplying every feature vector by some matrix W. So in GCN, the matrix W is the one that is learnable. So what is important that what I'm writing here is a continuous version of the GCN. When discretized with fixed step size tau, it becomes a residual version of the GCN. So in deep learning, this would be called a residual connection. So I'm bringing back the current state, and I'm changing, I'm updating it with the diffused and mixed version of my features. So this is one of the simplest graph neural networks. It is highly parallelizable. So one of the ways to scale it to large data sets is to pre-compute the diffused features, maybe with a few steps of diffusion, and then just learn these weights W. So what is common is to include also a nonlinearity if you use multiple layers. So you activate every component by, for example, ReLU activation function. It is also common to use different weights per layer. So this matrix W is dependent on T. And there is kind of statement that is repeated everywhere in the literature. So I would call it the GNN folklore, that it only works for homophilic data. And the reason that is usually given that it's, well, it's a low pass filter, right? So low pass filter is a low frequency dominated process. So it will work only if the labels of your neighbor nodes are similar to your own label, right? So you're mixing information of similar type. Now, I would like to challenge these last three assumptions, that we need nonlinearity, that we need different weights for layers, and that it only works for homophilic data. But I will start actually with the first question: when this kind of evolution is a gradient flow, right? So we've seen for the Dirichlet energy that the gradient flow is the diffusion equation. What would be some generalization of the Dirichlet energy that will have as gradient flow something that looks like a graph convolution. So this is the kind of energy we would like to study. So this is a parametric Dirichlet type energy. So we have two components here. So we have components that, so xi, I remind you, these are the node-wise features. So we have a component where xi interacts with each other through this inner product omega, right? And we also have another component that is pairwise interactions between nodes connected by edges. And here they're parameterized with the matrix W. So if you think of it as a physical system, we have pairwise interactions between nodes, and think of it as, for example, if we have particles, every node is a particle, then charged particles will attract or repel each other. The external part could be, for example, some drift or some force that acts on all the particles at the same time. Now, it's easy to write the gradient flow for this parametric energy. And what you notice when you take the gradient, you see that the matrices of parameters omega and W enter here in a symmetrized form, right? So from now on, without loss of generality, I can assume that these matrices are symmetric. So for gradient flow, it's important that the matrices of parameters are symmetric. You can also see that these matrices are independent on time, right? So I have the same omega and W for every time step t. So this is what in deep learning we call weight sharing. So every layer will be parameterized by the same set of parameters. Will not have a different omega and W at every layer. Now, what I can also do is to rewrite this energy when I decompose my matrix of weights W into components that have positive and negative eigenvalues. So I denote it by theta plus and theta minus. And if I do this decomposition, I actually have these components that the component with the positive eigenvalues induces attraction, and the component with the negative eigenvalues induces repulsion. So again, if you think of this as a system of particles, then we have these repulsion and attraction components, and you can think of it this way. So these are the nodes of the graph in the Fisher space, and as they evolve, they're along one of the directions in the Fisher space, in this case, the vertical one, they attract, and along the another direction, which here is horizontal, they repel. And you can actually see that this graph is heterophilic. So we have nodes of different types connected to each other, and nevertheless, we are able to separate it. So this is an important observation that I will formalize in a few seconds. But this is how it looks like. So it's very similar to what we've seen before. And this is a framework that we call GRAPH, standing for gradient flow framework. Again, as before, we've seen in the diffusion equation, we start with nonlinear encoding of the input features. Then we apply the linear gradient flow. So there is no nonlinear activation whatsoever. So this is the discretization of the gradient flow that we've seen before. So we have two parameters. We have W and we have omega. We have residual connection. The residual connection actually is important. And then we have nonlinear decoder. So I remind you that the three assumptions that are commonly done about GCN type architectures is that we need nonlinearities between layers. We don't have them here. What was the other one? They work only with homophilic data. So I will show you that this is not true anymore. We can actually deal with heterophilic data, and then we need to layer dependent weights. So you can see that these matrices are shared across layers. So the number of parameters is drastically smaller than in standard GCN. Now, if we do spectral analysis for this evolution equation, I assume here that omega equals to 0. So I get the standard GCN, and I use the eigenvectors and eigenvalues of the Laplacian and the channel mixing matrix. I denote them by phi lambda and psi mu, respectively. I can write the output of m layers of this framework in the form of this polynomial. And you see that what happens here is some kind of interaction between the eigenvalues of these two matrices. So I remind you that lambda are the eigenvalues of the Laplacian. So this is in harmonic analysis on graphs. This describes the frequency of the signal of the features, and mu are the eigenvalues of the channel mixing matrix. So what we see is that for low frequencies, they're normalized between 0 and 2 for the graph Laplacian. Low frequencies, meaning lambda smaller than 1, these are magnified by positive eigenvalues of W, right? Mu greater than 0. And high frequencies are magnified by negative eigenvalues of W. So basically, by choosing W with a trade-off between positive and negative eigenvalues, we can induce both high frequency and low frequency dynamic on the graph. So more formally, if the eigenvalues of W are sufficiently negative, then this framework is high frequency dominated, in the sense that the Dirichlet energy of the normalized solution will converge to something that is non-zero. So this will be half of the largest eigenvalue of the graph Laplacian. So what is important that basically we don't have oversmoothing phenomenon that is the folklore attributes to GCNs. So we don't have it here. So no oversmoothing. Now, another thing that you can do, you can also define the Fourier coefficients, right? And you can look at the evolution equation of this framework in the Fourier domain of the matrix W. And here you can see that along the eigenvectors of W, negative eigenvalues, if these eigenvectors correspond to negative eigenvalues, then the dynamics is equivalent to sign flipping along the edges. And this was one heuristic that was introduced recently in order to deal with heterophilic settings. And this is intuitively clear. So if I have a neighbor that is similar, that is dissimilar from me, I need to treat it differently. So, and one of the ways of doing it is introducing negative weights on the edges of the graph. Now, this is how the performance of this method looks like. And what is shown here is a node classification on a synthetic Cora dataset where we can modify the homophily of the graph from 0 to 1. So 1 meaning completely homophilic, so meaning that my neighbors are exactly like me. 0 meaning that my neighbors are completely different from me. And here the two extremes are the GCN. So GCN works extremely well in the very homophilic case, but once the homophily of the graph drops, then it performs poorly. And another extreme would be to completely ignore the graph, and we can use just an MLP, a multi-layer perceptron, for every node of the graph applied to the Fisher vector. And of course, you can see that, well, it doesn't depend on the homophily in the data set, but it doesn't take advantage of the graph structure in the high homophily cases. So it outperforms GCN in the regime of low homophily, but it underperforms GCN in the regime of high homophily. Graph, you can see that takes advantage of both worlds. So it is it can take advantage of the graph in the case of high homophily, but it also doesn't deteriorate when the homophily is low. And this is again breaks the folklore that GCNs are unable to cope with this case. So graph is essentially a convolutional type architecture. It just designed in a smart way that is a gradient flow of some generalized Dirichlet type energy. So we've seen already this picture, so I would like to look at it from different perspectives. So this was the evolution of the graph together with the features on the graph. And maybe for people coming from signal processing perspective, it looks a little bit disturbing because I'm doing some filtering on the graph, but the graph changes under my feet, right? So kind of shaky ground. But in differential geometry, this is actually very common to do these kind of processes, to evolve a domain, a manifold, by some kind of differential equation. And probably the most famous example of such equations are Ricci flows. And structurally, they look very much like the diffusion equation that we've seen before. So on the left-hand side, we have the temporal derivative of the Riemannian metric that locally models the structure of this manifold. On the right-hand side, we have a second-order quantity that is called the Ricci curvature tensor. So it's a little bit similar to the Laplacian. So overall, structurally, sometimes these equations are called the kind of diffusion of the Riemannian metric. Of course, they have different properties. And if you start with a manifold that looks like this dumbbell, so it has negative curvature in the middle and positive curvature on the ends, if I run this equation actually backwards in time, then this dumbbell becomes more like a sphere and then collapses into a point. And this story of Ricci flows was introduced by Richard Hamilton in the 80s with one single goal, is to prove the Poincare conjecture. So Poincare conjecture is a way of characterizing topological spheres, and on two-dimensional sphere, you can say that it's a sphere if you can take any closed curve, right, a one-dimensional sphere, and collapse it to a point. So you can extend it to higher dimensions, and the idea of Hamilton was that using this way, you can prove the Poincare conjecture that postulates the same property about high-dimensional spheres. And as you probably know, this mechanism was used by Grigori Perelman about 15 years ago to prove this conjecture. Actually, a slightly more general result that was a triumph in differential geometry and topology. Now, what does it have to do with graph neural networks, you may ask? So I remind you that I mentioned this problem of bottlenecks and oversquashing, and it comes from the fact that some graphs might not be efficient for message passing. So in particular, if I have a graph where the volume grows exponentially, in other words, if I look at the number of the neighbors of the neighbors of the neighbors, it will grow very fast in certain types of graphs. Trees are one example. Another example are small world networks, right? Like social networks like Twitter or Facebook. And if my task depends on long distance information, what happens is that I need to bring a lot of features from faraway nodes that are very numerous, and I need to squeeze them into a single feature vector that becomes very inefficient. So formally, I can formalize it in the following way, that if I have a multi-layer message passing type graph neural network that looks like this, so here I assume that the functions, right, that aggregation functions and update functions phi and psi are Lipschitz continuous, so alpha and beta will be the Lipschitz constants. I can define oversquashing as kind of lack of sensitivity. So if I'm looking at the output of the graph neural network at node I, and I'm changing the feature, the input feature at some remote node S, I want to see how the output depends on this input. And I can quantify it through this derivative, through the Jacobian of the output with respect to the input. And I can show that it can be bounded by some bound that depends on the Lipschitz constants, but also on the structure graph that enters here through a power of the normalized adjacency matrix. And intuitively, we understand that different graphs have this property differently acute nature, right? So trees are the most pathological example. Here, this bound will decay exponentially with the depth, but grids, for example, are pretty benign. So we need some more nuanced analysis that will allow us to distinguish between something that looks like a tree and something that looks like a grid. And that's exactly what Ricci curvature is designed for. So in differential geometry, it allows to classify locally the behavior of spaces, of surfaces, for example. So if I take two nearby points, P and Q, and I shoot geodesics from them in parallel, I can track them and ask whether they remain parallel, they diverge, or they converge. And respectively, I'm talking about something that is flat, zero curvature, Euclidean space. If the geodesics converge, then I'm talking about something that looks like a sphere with positive curvature. And then if they diverge, I'm talking about hyperbolic space. So this is what Peter mentioned in the beginning. The first examples of non-Euclidean geometries were actually hyperbolic geometries with negative curvature. So I can define something similar in graphs. So there are several constructions of the discrete analogs of Ricci curvature. One intuitive way of thinking of what would be an analogy of Ricci curvature, I can take an edge and two endpoints P and Q, and I can look at edges that emanate from these nodes P and Q. If they tend to form triangles, I look at something like a clique. So this is analogous to geodesics that converge. So we can call this positive curvature. If they tend to form rectangles, so this is kind of remaining parallel, right? So we have zero curvature. And in trees, they actually diverge, so they don't form any of these objects. So we are talking about negatively curved structures. So we use a definition that we call balance form and curvature. So it's defined for every edge of the graph. It doesn't really matter how it's defined. So it's combinatorial construction. You need to count the certain types of rectangles and triangles. that enclose the edge allow me to skip these details. What is important is that it reproduces the continuous behavior that we've seen before. So click-like objects are positively curved, grids are zero curved, and trees are negatively curved. And the main result is that if I have a graph that has many edges that are too negatively curved, so in other words, the Ricci curvature of these edges is bounded by a certain number that I call delta, then we can write an upper bound on this Jacobian that we've seen before. In other words, the over-squashing phenomenon, this lack of sensitivity of the output to the input comes from negatively curved edges in the graph. And once we understand it, we can try to rewire the graph by surgically removing these negatively curved edges and replacing them with edges with positive curvature, possibly in a stochastic way. And this is just one maybe simple and naive way of doing it. Actually, Petter had a follow-up paper where they suggested another construction that is based on expander graphs. And I think you can provide some more details about this. But bottom line, this rewiring improves the learning abilities of graph neural networks. So in this case, the graph becomes more friendly for message passing, and graph neural networks suffer less. And what is important that this method, it touches the graph very little. It is also suitable for both homophilic and heterophilic settings when the neighbors are different from the node itself. So in the remaining time, let me just mention one slightly more exotic thing is we don't need to stick to the graph to do diffusion, right? We can take the graph and actually lift it into a more complicated object. And again, I would refer to the question that was asked, can we do geometric deep learning on objects that are more general than graphs? So here's an example of an object that is more general than a graph, and it's called a cellular sheaf. So what are cellular sheaves? Without going too much into details, basically, you can take a graph and attach a vector space to every node and every edge, and then you have linear maps that map between these spaces, that connect vectors in these spaces. So an analogy in differential geometry is what is called an affine connection. So manifolds as graphs are purely topological objects, right? So in other words, we have only the notion of neighborhood, but we don't have notions of distances or angles. So manifolds are locally Euclidean. So around every point, you can associate a Euclidean space that is called the tangent space. So you can give geometry to a manifold by saying how to connect these tangent spaces between nearby points. And this is, as the name suggests, is called a connection. So connection allows you to do parallel transport on the manifold. And if you have a Riemannian metric, so that's the typical way of assigning geometry to a manifold, then there is a unique special connection that is compatible with the metric and has zero torsion, which is called the Levi-Civita connection. So same way you can think of this sheaf structure as giving geometry to your graph. And basically what we can do is we can make up the sheaf, we can actually make it learnable, and we can ask the question is, if I upgrade this graph to a sheaf structure, I can make this sheaf in many different ways. So what would be the right way of creating this sheaf in a way that will solve, for example, node classification problems? So in other words, we can talk about the expressive power of graph neural networks on when we lift the graph into a cellular sheaf by doing simple linear diffusion, running it to infinity, and then we restrict the class of sheaves by restricting the transformations between the vector spaces that we have on our nodes and on our edges, for example, to orthogonal matrices or maybe some other types of matrices. And in this case, we can get results about what kind of classification problems can be solved. So, for example, in GCN type architectures, when we have scalar transport maps and they are symmetric, we can achieve separation in homophilic settings. But if the graph is heterophilic, this kind of architecture is not powerful enough. And this is not a contradiction to the previous result that I showed you, because here we do not allow for channel mixing. So these are scalar transport maps. So heterophilic setting requires asymmetric transport maps, So when we have neighbor nodes from different classes, and this is exactly the mechanism of negatively weighted edges that we recovered from different considerations with the gradient flow framework. And you can also ask the question if we can use restriction maps of a higher dimension, or for example restrict them to orthogonal maps. But this gives an interesting alternative to the standard Weisfeld-Lehmann hierarchy. So the typical way of reasoning about the expressive power of graph neural networks and what kind of tasks they can solve or what kind of functions they can express is this analogy between message passing and the Weisfeld-Lehmann graph isomorphism test. So here we can say that instead we have a continuous version. So we can, for example, look at the limit of a diffusion equation with certain underlying object, the class of shifts that we are considering, and formulate the separation ability of this neural network in this way. So it completely departs from the Weisfeld-Lehmann formalism. Now, as I mentioned in the beginning, we don't necessarily need to consider diffusion equations. So here's an example. This was actually a collaboration with colleagues from ETH Zurich, where instead of diffusion equations, we considered second-order equations where we also have a kinetic term, so second-order derivative in time. And in this case, it's a combination of oscillatory phenomena, so wave equation with dissipation, so some form of dampening. And this is called graph-con, or graph-coupled oscillators. It actually we obtain quite good results on, for example, molecular graph classification. Now, I would like to finish with these memes that was posted on Twitter by Michael Galkin, that maybe makes fun of some of the recent works that where we used maybe a little bit exotic constructions such as message passing on cellular or simplicial complexes, or Ricci flows, or shift diffusion, whereas the more popular approaches in the graph neural network communities are simple methods such as graph convolutional networks. And here we bring this big axe of algebraic topology and differential geometry. So I think one conclusion that we've seen from the gradient flow formalism is that actually GCN is still a powerful framework. You don't need to necessarily discard it. Simple doesn't mean bad. Actually, it can solve many problems, and it can work in many situations that maybe the folklore attributes as impossible. So GCNs reivindicate themselves and can still fight back. So let me finish this with conclusions, and then we can I will be happy to answer questions. So I think there are many new interesting links between graph neural networks, differential equations, and consequently differential geometry and algebraic topology. It's a new set of tools that probably better known in this community of science, a new perspective of looking on graph machine learning problems. And it gives many formal and principled ways of approaching problems such as positional encoding, graph rewiring, over smoothing, dealing with heterophilic data bottlenecks, and so on and so forth. So we'll be happy to publish the slides and answer any questions offline. I actually got an email with a request to share the slides, so we'll put them on the website geometricdeeplearning.com.